This video is reviewing P2.2. So P2.2 is the middle section of P2 for GCSE physics, and it is focusing on Newton's laws. And so this section mostly focuses on forces. So first thing you need to know is some absolute basics about Newton's laws themselves. So Newton had 3 laws of motion. Okay, so the first law of motion is that an object at rest or in constant motion, so that we call that in equilibrium. So equilibrium can be at rest when the velocity is 0 or in constant speed. Either of those two scenarios will stay at equilibrium until acted upon by an unbalanced force. So I call Newton's first law the law of balanced forces, because it basically tells you what will happen in the case of balanced forces. So it says if the resultant force on an object is 0, then that means the resultant acceleration is going to be 0, and so the final speed of the object will be constant. Right? So resultant force leads to a resultant acceleration of 0. There's going to be no change in speed. So an example of where you can see this practically is, imagine we were in space and I got a spacecraft and I was to travel from the moon to the Earth. Obviously my rocket is going to leave the Earth, and when it gets into space, it's obviously going to travel all the way to the moon. Okay, but the actual booster doesn't need to fire. So once it's got into space and it's got up to speed, what happens then is the boosters turn off and the spacecraft will continue at constant speed without any extra fuel being burnt or any extra additional force being applied, because in space there is no friction. So because there's no friction, there's nothing to slow this object down. In our everyday experience, we don't really see Newton's first law because of friction getting in the way. Newton's second law is what I call the law of unbalanced forces. Okay, and basically what it does is it tells you what will happen when the resultant force is not 0. So when the way Newton wrote his law is he said that force is directly proportional to the rate of, which means divided by time, change of momentum. That was the way Newton wrote the law. So we have that equation, and that leads to the other equation we most commonly associate with Newton's second law, which is F equals ma. So force is mass times acceleration. So we have 2 equations there that we could use in calculations that are expressions of Newton's second law. But we can also write the outcomes of this in a slightly different way. So if there is now a resultant force, okay, that is going to cause one of 4 things to happen. It can cause an acceleration, so it can cause an object to speed up. It can cause the opposite of that. It can cause a deceleration, so it can cause an object to slow down. It can cause an object to change direction, because remember, acceleration and force are both vectors, so they have both direction and magnitude. And lastly, it can cause an object to change shape. Okay, so any one of those 4 outcomes is likely if there is a resultant force. And again, Newton's second law is that force is directly proportional to the rate of change of momentum. Newton's third law is the law of pairs. So this law is most commonly known as every action has an equal and opposite reaction. However, to understand this a little bit more, we need to add a little bit to this. This isn't sufficient. What Newton's actually said for his third law is that when you've got 2 objects, so for example, I might have a tennis racket and I've got a ball, and obviously as the ball comes into contact with the tennis racket, these are my 2 objects, A and B. Okay, so when object A exerts a force on object B exerts a force back on A. That is equal in magnitude. So that means it's got the same size. So equal in magnitude. opposite in direction, and lastly, of the same type. So the same type of force. So if this is a normal force when they're in contact, then there will be a normal force on the ball, on the racket, and there will be a normal force on the racket because of the ball. So what you can do is swap these two objects around. So an example of this that you might think of is if I've got a man firing a gun, and he's going to fire a bullet out of the gun, okay, like that. Obviously, during his shot, the gun is going to experience a force backwards, and the bullet is going to experience a force forwards. Those forces are equal in magnitude, but opposite in direction, and they're both the same type. Interestingly, because the mass of the rifle is a lot bigger than the mass of the bullet, the acceleration of these two objects is not the same, but the force is. So the acceleration of the bullet is going to be a lot faster than the acceleration of the rifle, but they will be equal and opposite. We could show this as a force time graph for two objects. So I could have, if I set this as my 0 line, if I've got object A colliding with object B, I would have a graph that would look like that for object A and B. So this would be object A, this would be object B, and you can see the area of this graph, which is the change in momentum, because it's force times the change in time, that is equal. So equal but opposite, so it's a minus, and of the same type as well. So it's from that you then get the conservation of momentum. Just another point about forces in general now is in terms of the different types of forces you have. So you can have two basic categories of forces. You can have forces that are non-contact forces, so things like gravity would be an example of that. So I could show that on a ball as the weight, as the force acting downwards. So the equation for weight is mass times g, where g is the acceleration due to gravity, and that is an expression of Newton's second law. It's a special case of F equals ma. So we could have gravity as one. If I'd got two magnets, for example, and I've got two north magnets, two poles rather, of facing each other, so opposites will repel, so they're both going to experience a force acting outwards. That will be a magnetic force. So again, that's a non-contact force. And charged objects also do the same. And then you have contact forces. So for example, if I've got a box moving along the surface of something, then that's going to cause friction. So friction is going to move along the base of the surface. And you can also have air resistance as well. And remember, friction always acts in the opposite direction to the way something is moving. Another example would be if I've got any objects in contact, we have the normal force. The normal force always acts 90 degrees from the surface. Okay, and is sometimes called the contact or reaction force. So it's always 90 degrees to the surface. So if I've got a block on a slope, the normal force would be in that direction. So there's lots of different types of forces: friction, drag. In the case of skydiving, which I'll just mention, or any falling object, we only ever focus on two forces. We focus on the weight acting downwards, and we focus on the drag acting upwards. And when those two forces are equal, then you have an object that is at terminal velocity. Now, if you don't know how skydiving works, there is a whole video focused entirely on skydiving, so make sure you go and watch that. So what we can do is, because forces are vectors, the direction matters. So for example, if I've got a force on a box and I've got 20 newtons that way, obviously Newton being the unit of force, and 10 newtons that way, my resultant force is going to be 10 newtons in that direction. So it's very straightforward when the forces are in the same plane. If you've got a force, however, that is at an angle like that, so let's just say that's 5 newtons, okay, then what we can do is, to simplify this force, we can break it into two components. So we can break it into a horizontal component, which would be 3 newtons, and we could break it into a vertical component, which may be 4 newtons. Okay, so you can break forces down like that. If you're asked to do that in your exam, what you would most likely be asked to do is to put it onto a scale drawing. So, for example, you might have a like a grid in your exam. It's just a very crude representation, and you may be asked to start at this point, for example, and the resultant force is like that. Well, what you could do is you could break that down into 2 that way and 3 that way, okay, and show the forces broken up like so. And you can use Pythagoras to work that out. So remember, Pythagoras' theorem is the square of the hypotenuse is equal to the sum of the square of the other two sides. So 3 squared plus 4 squared, which is 9 plus 16, gives you 25, which if you square root gives you 5. So there are lots of other examples of that you could use that would also work. So you could use Pythagoras to calculate the resultant force in that case. So just in summary of this, what we've covered so far, so we've got Newton's 3 laws. Newton's first law is the law of balanced forces that says when an object at rest or at constant speed will stay at rest or at constant speed until acted upon by an external force. So if all the forces are balanced, the object is going to stay in its current state of motion. If the forces are unbalanced, Newton's second law, force is directly proportional to the rate of change of momentum, and therefore one of these 4 things will happen. It will accelerate, decelerate, change shape or change direction. And Newton's third law, every action has an equal and opposite reaction, but the equal in magnitude, opposite in direction, and of the same type. So just link to Newton's second law for a second. If we have a look at some of the equations that we could be asked to apply now. So in this particular section, we've already mentioned we have F equals ma. So force is mass times acceleration, force in newtons, mass in kilograms, acceleration in meters per second squared. We have momentum as another equation in this topic. So momentum is mass times velocity. This is the symbol for momentum, which is the Greek letter rho. The unit of momentum isn't named after anyone. It is just the unit of mass, which is kilograms, times the unit of velocity, which is meters per second. So that's the unit of momentum. And we can put that together like in this version here. So force is the rate of change of momentum, like so. And in this case, delta t is the duration of a collision. So momentum we apply in any situation where there is a collision. So as an example, if I've got 2 objects and they are going to collide, okay, and at some time later they're going to bounce off each other in that direction, what we can say is we can apply the principle of conservation of momentum, which says if I add up the momentum of each of these objects, so if I call this A and this B, so at the start the momentum of object A will be its mass times its initial velocity. So the mass of A times the initial velocity of A is its momentum, plus the momentum of object B, which is the mass of B times the initial velocity of B. That is going to be equal to the mass of object A times the final velocity of A, that's its final momentum, plus the mass of object B times the final velocity of B. And what I can also do is I can have 2 other situations for momentum collisions where I have objects that either stick together, and if they stick together, this equation is exactly the same, but the second bit becomes ma plus b v for the whole object. And the other situation I could have is an explosion, which again is the same as this equation at the top, but the first bit starts with the 2 bits together and their initial speed, and the final bit would be the same, so the 2 bits coming outwards. So that's just a bit about momentum and the different equations you could be asked to apply for those. Remember, again, I've mentioned skydiving. That is a big part of this. So again, watch the video on skydiving. You have to be able to explain the 5 stages of a skydive. Principle of conservation of momentum, we've talked about here. It comes from Newton's third law. But just to summarise, the principle of conservation of momentum, which is shown here, is that the momentum before a collision will be equal to the momentum after a collision. Okay, so the total momentum is constant, it is conserved, same as conservation of energy. Other equations that are in this section, not related to force explicitly or momentum. So we have the first introduction of the equation for work done. So work done is another way of saying energy. So work done and energy are synonymous with each other and obviously measured in joules. That is the force multiplied by the distance travelled in the direction of that force. So as an example, if I've got an escalator, for example, and I've got a lady who's going to work up the escalator, if I've been told her weight, so obviously a weight is the force due to gravity acting downwards, I could be given in the question two distances, the distance up the escalator or the height of the escalator. And it's the height that I would need to use because the force is in the vertical direction, so I need a vertical distance. If I had the same situation, but this time, just as a contrast, I've got the escalator, I've got my person at the bottom, and this time I've been given the force that the escalator exerts on the person this way, then it would be okay to use that distance, the distance height, rather than the height. So in this case, I wouldn't use that, I would use the height. In this case, I would use the distance. So it's force times distance travelled. So this is, effectively, it's the displacement. So it's the distance travelled in the direction of that force. Okay, so that bit, massively important. Once we've got the equation for work done, we then get the equation for power. So power is the rate of energy transfer. So power is measured in watts. Energy or work done is obviously in joules, and T is time in seconds. In this topic, there's also an equation for mechanical power, because what we can do is we can put these two equations together. So we can get power is energy divided by time. We know that energy is force times distance divided by time, and distance divided by time is speed. So speed or velocity is displacement divided by time. So you get a new equation for power, which is specific to mechanical power. So when we talk about mechanics, more mechanical power, we're talking about any situation that involves a force. So we have this equation specifically for mechanical power, which is power is force times velocity. And velocity is the same as speed, but it has a direction. So that makes a difference. The last little thing just to mention in this section is circular motion. And you don't need to know a great deal about this, but you are expected to know that for an object travelling in a circle, that, let's say, for example, I've got the sun here and I've got the earth at a point here. For an object to travel in a circle, there has to be a force acting towards the centre of that circle. So if this earth was to come around here sometime later, the force would still be acting to the centre. And that force is called the centripetal force. Okay, and that isn't a special force. It can be any of the types of forces we mentioned. So for example, if it's a racetrack and it's a car, and I apologise for my terrible drawing of a car. It really is a terrible drawing of a car today. Right? So imagine those are the tyres. It's terrible. But you can obviously imagine the car is turning the corner. So there is friction by the tyres acting towards the centre of this circle. So there's always a force towards the centre, that is the centripetal force, but it's caused in this case by gravity, in this case by friction. There is no such thing as centrifugal force. So they might include that in your exam. Fugal force is a word that's often used, but fugal is fake. It's not a real thing, so don't confuse it with centrifugal force. The word that we are looking for circular motion is centripetal. And because there is a resultant force causing this, when something travels in a circle, your speed is constant, but you are still accelerating because you are changing direction. And so when there is a resultant force, you can change direction, like in a circle, without necessarily speeding up or slowing down. So that's just a brief overview of all the bits of P2.2. There are a lot of quite deep concepts in this little section that will appear in multiple places across the rest of your exam. The first thing I would make sure you look at is the equations. Make sure that you've learnt those. Look at Newton's laws, and then you take the bit information that's here and check out more of our videos on any of the different bits to help this make more sense. So you can check out videos on skydiving, which if you don't know, please go and do. Link to distance time graphs and speed time graphs, again, check out the videos on that. There are videos on free body notation and how to draw and label forces in more detail as well, so have a look at that. And we also have a video going into quite a lot of detail about momentum. So for GCSE level, it's worth watching the first part of that video, and then it very quickly progresses beyond that. So just watch the first part of our momentum video as well to help you in that section.